Alright, so you need a little help with crazy friction problems, also known as what we're going over on page 139. And while I don't have the exact problems written down from page 139, I do remember the basics, at least of number one, and I can tell you a number of things that probably help with number four. So when you think about it, in these problems, in all these problems, it's going to be very easy to figure out one force definitely, and that is going to be the force of gravity. Force of gravity. It's going to be force of gravity, and because you're almost always going to be given mass to work with, so you can figure out force of gravity. So I'm imagining a little problem here. I'm going to give you a mass of 2.55 kilograms, and the reason I do that, because you multiply that by g, you get a force of gravity of 25 newtons. Nice and easy number to work with. So that's the easy part. What makes these problems different is that you have forces that are upwards or downwards in addition to be going forward and backward. So what if this was like our shopping cart from class? Here, now it's a shopping cart. And we're pushing down on the shopping cart at, let me make up a vector here. Let's just say that we're pushing down on it at a very shallow angle. Okay, and I'm completely making up numbers here. You got your angle there given in the problem. Well, you would then say, well, we know that we are pushing forward on the cart and we are pushing down on the cart. So if I call this original one force applied, well, then I'm going to call this one here force applied Y and force applied X. So I'm going to use SOHCAHTOA and break that down. And since I'm making up numbers anyway, I'm going to call force applied Y 10 newtons and force applied X 25 newtons. That's the beautiful thing about making things up. So this is stuff that should be supplied in a problem. And before you even worry about what the rest of the problem is, you have enough data to be able to figure out normal force. Remember how we talked about if you're pushing down on the cart, the ground has to support both the downward push and the force of gravity? Well, that ground supporting it is normal force. So we're going to say if the ground has to do both, we are going to simply add these two up and get our normal force. Force normal. And it's going to be the 25 newtons from gravity plus the 10 newtons for the applied force, and so that's going to be 35 newtons. And this is the juncture where the problems start to differ. Maybe I think in the homework number one they give you the coefficient of friction, and so you need to find the friction force. If I'm not mistaken, the cart or box, whatever, is accelerating in problem number one. Well, what that tells us is that the force of kinetic friction is not as big as the applied force. So there's a net force forward and it's accelerating. And we need to figure out what that force of friction is in order to be able to calculate it. And so you come over and you use your friction equation. Force of kinetic friction is equal to coefficient of kinetic friction times force normal. Well, we got force normal, 35 newtons. And in the problem, they would supply you with the coefficient of friction in this case. I'm just going to randomly make one up. 0.6 is my coefficient of friction. And I'm going to calculate that, and you put it in the calculator, and you get a big old 21 newtons. That's an N, I swear to God. So you found the forces, and that's really the big deal in these problems, is finding all the forces. And what you have to do then is you have to say, all right, 25 newtons and 21 newtons, there's an imbalance, which means it's not in equilibrium. It is accelerating. There is a net force. And so you're going to say force net is, applied force, 25, minus resistance force, 21, and you end up with 4 newtons of net force. And then if the problem's asking you about acceleration, well, then you go to Newton's second law, where net force is equal to ma. 4 newtons is equal to 2.55 kilograms times a, and you would divide by 2.55, leaving you with a mythical 1.57 meters per square second. So let's backtrack. How do we do it? Find the force of gravity. Should be able to do that in every problem. Draw the applied force. Break it into x and y components. Then you have to evaluate how you get normal force. In this case, we had a down and a down, so we needed a bigger upward force for normal force. Now that said, you could very easily, it could come out a different way, where here's your box, you've got force of gravity, no problem. But what if we take the exact same vector just off at an upward angle, we still have 25 there and 10 there. If it's the exact same vector just up instead of down, well, now the ground, it has to support 25 because of force of gravity, but you're helping out. You're doing 10 newtons of that work, and therefore the ground doesn't have to do that the whole amount. The ground normal force only has to do 15 newtons because up 10 and 15 equals down 25. So that's a way the problem can be different, is you could be upwards. The other way is they could say that your box is moving with a constant velocity, which would indicate that forward and backward are equal to one another, 25 newtons. And they would ask you to find the coefficient of friction. So you'd have 25 newtons equals coefficient of friction times 35 newtons. I'm sorry, whoa. My bad. Normal force is only 15 newtons. And then they say find the coefficient of friction, and you'd have to just divide 25 by 15, and you'd have a crazy big, over 1 coefficient of friction. And that's just kind of the different ways those problems work out. The big key here, the big thing, is normal force. Normal force. How you get normal force? You either need to add the 2 down arrows and balance them out with an upward arrow, or you need to take 2 up arrows and balance them out with 1 down arrow. I hope that's helpful. Please revisit that homework assignment so that we can go over it and many of its friends in the coming days.